Good afternoon and welcome back to the 22nd Annual CERIAS Security Symposium, live from Purdue University. Next on the agenda is our panel discussion on trusted microelectronics, the base upon which all connections are built. My honor to introduce each of our panelists, Sunil Cheruvu, who is the Chief IoT Edge Security Architect and Senior Engineer with Intel. Intel is a proud partner of CERIAS. Diane Walters, Principal Embedded Security Engineer with MITRE. MITRE also has a seat on the CERIAS Advisory Board. And then two of our esteemed faculty members, Professor Peter Bermel, the Elmore Associate Professor of Electrical and Computer Engineering here at Purdue, and Anand Raghunathan, the Silicon Valley Professor of Electrical and Computer Engineering here at University. And our moderator for this panel is Professor Eugene Spafford. Spaff, the floor is yours.
Well, thank you. It's a virtual floor, of course, as we are all here online. So welcome to everyone who's tuning in, and certainly welcome to the panel. We're going to start off with some brief remarks from each of our panelists, and then we'll jump into some discussion. If you're in the audience and you have some questions for the panel, please post them in the Q&A section and I'll get to them and relay them to the panel. So looking here on my screen, Anand, you're my first person into the panel on the list. So could I get you to make your opening remarks first, please?
Absolutely. First of all, it's an honor to be here on this panel. Thanks for inviting me, Dongyan, and welcome all the other panelists. Look forward to an interesting discussion. By way of background, as was mentioned, I'm a faculty member here in the School of Electrical and Computer Engineering. I spent roughly the first half of my career in the industry. I was working for NEC Corporation, working on among a range of topics relevant to this panel, focusing on security architecture of mobile application processors. So, I was part of a team that developed the security architecture that went into 3 generations of NEC's products. So learned a lot about, concerns from security concerns and how they permeate down to hardware. Through that experience at Purdue, I've been involved in various initiatives, research initiatives since fall of 2008 when I came here. Notably, now I am co-directing a newly launched center called the Center for Secure Microelectronics, which is specifically focused on how we design chips assuming a zero trust model. We'll be talking about that more, I assume. And I've also looked at other security in the context of other classes of embedded systems like medical devices in my research here at Purdue. So that's by way of background. In terms of my thoughts, I think clearly the reason we are there's multiple reasons secure microelectronics is an important topic today. One is, of course, as from the perspective of end users, we would like secure computing systems. A lot of it, of course, starts with the foundational security primitives, cryptography and all of the other functional mechanisms that go into making a system secure. But eventually, they need to be embodied in secure implementations, all the way down to the hardware. So I think the hardware can be both a source of vulnerabilities, part of the attack surface, as well as part of the solution. Meaning that thereby that you can actually build in mechanisms in the hardware that prevent or help you defend against software vulnerabilities and software attacks. Now, more recently, I'd say maybe in the last decade or so, there's been increasing concern about the global disaggregation of the chip design and fabrication chain. So if you look at the global footprint of a chip, a microelectronic system, from the acquisition of IP, intellectual property blocks that get assembled into a design, into a system on chip, to the actual design process, and then the fabrication, packaging, test. A chip might see if you trace a global footprint of the different entities and geographies involved, it's pretty global. And so that leads to naturally a lot of concerns about the potential for new threats and new vulnerabilities being introduced, particularly in critical systems. And so at our center, that's one of the areas we are specifically focused on, trying to design chips under a zero trust model. For example, if the entity designing the chip doesn't necessarily trust the entity fabricating the chip, and so on and so forth. So I think that is another important reason why secure microelectronics is becoming an important topic. Let me stop it there and hand it over to my co-panelists.
Thank you. Let's see. Sunil, could we ask you to make your remarks next?
Yes, absolutely. And I think, first of all, thank you for this opportunity. It's the first time for me to come into your particular CERIAS 2021 or CERIAS panel. And Anand, I think you are absolutely right. It all starts with the hardware. And what I always like to say, when we meet with customers and we try to design solutions, the hardware is either, no matter how you look at it, it's either first line of defense or last line of defense, right? So when everything goes, gets compromised, you go down layer by layer, and the layer where you have to take a stand and defend is hardware, right? So if hardware is compromised, everything is compromised. And so briefly about myself, I lead a security architecture team at Intel in the Network Edge group, and within that, I'm part of Internet of Things group. And this is absolutely near and dear to us because we actually, pretty much Internet of Things group deploys products in the Atom, Core, and Xeon, and accelerators. So very, very close to us. And we have seen, requests from our customers on anti-cloning capabilities. We have seen, certain silicon, getting kind of cloned, and they showed up in the markets. We are aware of that too. We were in the middle of some other incidents as well. But when you look at all of those, my team is chartered with mitigating, the threats that are originating as part of the IoT and the edge. So it's a broader threat surface and trust boundaries, right? Amorphous trust boundaries. And then at Intel, first of all, Intel is invested and leading the industry in hardware supply chain assurance with transparent supply chain. Now, what is transparent supply chain? That's a service that actually enables you to get some visibility and also attain traceability of hardware components and firmware along with the systems, right? And where does that start? That starts in the on the factory floor, and the PC and server manufacturers can take advantage of that. And not only that, you can enhance the visibility and attain traceability, you can also make sure that the authenticity of the firmware is ensured. Now, we have other mechanisms where at runtime, you could use verified boot, measured boot, or secure boot as a whole to ensure that you are booting, firmware, known good firmware. But how do you ensure that, first of all, the known good firmware gets on the platform and stays on the platform? Right, so that's part of the supply chain. And then some of the key features of this transparent supply chain capability include the security, of course, cryptographic verification of the authenticity, and then traceability, and again, tying all these measurements back to a trusted platform module. That's how you tether it back. And then the accountability, where there is something called platform data file that gets generated, and that can be used to verify against. And that's the last part, that is the assurance part of it, right? So, and we have this service available for, let me see, commercial, Core i3 and above, and all Xeon SP, the scalable. So you do have these across, variety of platforms if you really want to test it. And so that's what we are investing in, and we are investing in some other things as well. But we can go into those as we continue. So we'll pause there.
Thank you very much. Peter, well,
yes.
You next.
Okay, so first of all, thanks again for the invitation. It's an honor to be here, and I thank all the audience for listening. So let me explain a little bit about my perspective on trusted microelectronics. So first of all, I think Joel kind of alluded to this. Software and applications all fundamentally rely on having trustworthy and reliable hardware. So therefore, even if we're primarily software people, we still have to think about like how the hardware affects the capabilities that we have and the level of security and trust that we have. And there are a lot of challenges in this field. I mean, it's certainly an open field for both research and all kinds of practical solutions as well. So a few examples include, you could call it kind of a group of malicious type behaviors. And I'm sure you've heard a lot about these in the news, things like botnets, which oftentimes run off of devices that are not completely secure. Things, Internet of Things type devices that have IPs, but don't necessarily have a good way of having like updated security capabilities or patches are a big challenge, and that can drive all kinds of cyber attacks, including Trojans, distributed denial of service, and so on. And so the fundamental challenge there is that you have lots of internet connected devices that are not inherently secure. So that is a huge challenge. It's not easy to solve it because obviously that's not the intent of the manufacturers, but it can happen. And having a better way to patch those devices and otherwise make them more secure is an open question of how we can do that in a way that's both practical and cost effective, and can also theoretically prove that it's more secure than the current approach. And so, of course, the most dramatic examples that have come into the news recently have been kind of on the interface between software and hardware, things like cyber physical attacks on infrastructure. You've heard a lot about the Colonial Pipeline ransomware attack. That was a huge news story because it basically was affecting like the ability of the US public to access gasoline and other vital supplies, right, which are driven by the presence of energy, right? So it does illustrate just how critical that is. And I think you could argue that this is primarily like a software type problem, but you could also make the argument that having like better hardware-based approaches to securing those types of systems could reduce the chance and severity of those sort of attacks. So I think that is a big open question for researchers. Again, how do we make this less likely to happen in the future? And that is not something I'm going to answer today, but I just wanted to mention that I think that that has to be a big priority, like because it's in the public interest to secure those types of critical cyber infrastructure systems, and also to just reduce the chance that this could happen in the future. Then there's a second category of attacks that doesn't, issues, excuse me, that don't necessarily get as much attention, but are still important. And you could kind of call this like, rapid obsolescence or unexpected failure. And there are lots of examples of this. And one case where this can happen a lot is when you take off-the-shelf components that have been tested in particular environments, and then you put them somewhere else. So when you put these types of electronics into extreme environments, whether they be outer space or another planet, or even somewhere on the Earth that is fairly different from a normal office environment, say like deep underwater, or in like a very low pressure environment, then lots of things can happen that are unexpected. And so being able to understand what are the mechanisms by which these failures can take place and what are mitigation methods to address them can help. So just to give you a brief explanation of my background and what I'm working on now, I have led in the past this ASSURE program, which was funded by Indiana Innovation Institute, IN3, and it addressed three major areas to address some of these hardware trust gaps, including developing novel hardware that works in a zero trust environment. So that's related to what Dr. Raghunathan talked about, ultra reliable hardware that can survive these extreme conditions, as well as anti-counterfeiting measures. And currently I'm leading SCALE, which is a Department of Defense funded project on developing a workforce for students entrusted in assured microelectronics, which has an emphasis on the hardware side, but also includes a component of artificial intelligence and how that relates to the hardware. So thank you for your time, and I pass it on to the next panel.
Thank you, Peter. And our next panelist is Dan Walters. So Dan, could you give us an opening statement, please?
Sure. I'm Dan Walters. Happy to be here. I'm an embedded security engineer at the MITRE Corporation, where I've been for about 15 years. During that time, I've taken on a number of different roles, from principal investigator of internal research to supporting some of MITRE's sponsors directly across the DoD and elsewhere to protect their systems. One of my current roles is to lead MITRE's efforts across the corporation in helping to secure the microelectronic supply chain. So I'm very happy to be here to talk about that. And I got to say, I've worked on a large variety of projects in embedded security, many of which were really hard to do. But I think this problem of trusted microelectronics is one of the hardest problems facing our country and facing the world today. It turns out, as hard as building secure embedded systems is, it gets even harder when you open up the threat model. What do I mean by that? I like to tease my colleagues who work in cybersecurity on more traditional systems, things like desktops and servers and networked systems, because I say, your job's easy. All you need to worry about is attackers that have this very limited scope. They're going to attack your system over the network. So secure your software and you're good. And right. And of course, it's not that easy. But when you compare a traditional system to an embedded system, that threat model, it really is true that it's much more limited. With an embedded system, the types of things that I'm often working with, I have to not only think about all the software vulnerabilities that system might have, but also the hardware vulnerabilities, things that an attacker can do if they have physical hands on your device or can at least get close to it. And there's a lot of other things that then you have to consider with that. So in that way, when you open up the threat model, the scope of the things that your attacker can do, it really changes the game from the defense standpoint of what you got to worry about. And now, you get to secure microelectronics, and what we're talking about is really completely opening it up, because almost every secure design is going to start with some root of trust, and that's the base from which you build upon, right? And so when you open it up to say, now I'm not sure that I even have that root of trust, right? Because the people that are creating, that are building my trusted system for me through the fabrication of the microelectronics are no longer trusted entirely, to where I don't know that the hardware that I'm building on does what I think it does. Right? That now becomes a seemingly impossible situation to try to build trusted systems on. And that's the question. How do you build this trusted system if you don't trust the foundation upon which it's built? And unfortunately, that's the situation that the world is in, right? The supply chain has become so consolidated into where the whole world relies on just a few entities to produce their advanced microelectronics. And it's really not as simple as just reproducing that, right? We can't just build more fabs here and elsewhere to reproduce and try to get to a self-sustained or self-sufficient supply chain, because the market is just so complex. If you try to do that, you'll lose a lot of money, and so we need something more than that. And it's really hard to know what that is. So I think that's what we're going to talk about, is what more do we need? How do we get there? And looking forward to the conversation.
Thanks. Let me just make a few remarks here to help set the stage a little for some in the audience who may not have the background in this. When in particular, when Dan is making note that it's not easy to set up a new fab, it's possible to set up a fab, but at die sizes, or that is at the level of packing on a chip, that I'm 20 years old. To use the very latest technology is incredibly expensive, both for getting the X-ray lithography kind of equipment in place that to cut the masks for the chips, the purity of the material required, the clean rooms, the other kinds of processes involved are extraordinarily expensive. And unless you are willing to continue to capitalize in this arena to build out your capacity as you go, it gets more and more expensive. A second point that was raised here, and you heard this from a couple of the speakers, has to do with supply chain and where chips are made. There are some selected foundries in various places around the world. And again, it's not easy to just create new ones in a new locale, not only because of the equipment, but for the expertise of the people involved. And there are environmental issues because of some of the waste, the water that's required for cooling and other kinds of issues. So we have some companies that make the designs, the masks that are for the high-end chips that are then produced at foundries that are run by other firms under contract. So that adds to some of the complexity of determining if what is produced is actually what was designed. And of course, then there are the issues of the design tools. To give an idea here, and this actually leads into my first question, back in 1974, when the 8088, or what was it, the 88, but that first chip, the 8080 chip came out that Intel had, that had 6,000 transistors on it. The M1 Max Pro that Apple just released has almost 34 billion transistors on the chip. We know from security studies that complexity is the enemy of good security, and how to even test and assure chips with that much functionality on them becomes an incredible problem. And so I'd like to get some comments on that. And I'll ask Sunil to weigh in on that first, because I happened to mention the Intel 8080 chips there, and we'll give you a shot at that first.
Yeah, that's a very good question, and I think that's the next $1 billion or even $1 trillion question as we get into the complexity. I think if you start beginning to slice it, I would say at least the way how we are looking at it, or if semiconductor manufacturer is looking at it, is divided into different phases, right? So when you look at the life cycle or the supply chain life cycle, you have the design phase, right? A conceptual phase followed by design. And I think in the design phase, there are some things that you can consider. You can take a closer look at the third party plugins that get into it, the design tools themselves, and also get a good idea of the insider threats is, I think I would say that's another thing. And we are also seeing that we could focus on attack on the design, networks themselves, right? So that's one thing. So to actually slice it. And then during the integration, again, there is a focus on insider threats, a thorough threat modeling. And then there's an idea and focus on malicious hardware, of course, and firmware that also goes into it. That's part of the integration. And then the ability to detect any kind of design alteration is another thing that we are also looking at when we are again slicing this, right? And unauthorized disclosure is another part. But when you start beginning to get into manufacturing phase in the life cycle, absolutely, the Trojan circuitry is part of it. Component replacement is also part of the complexity. So. And we are even talking about the SOC. Within the SOC, I didn't even go outside of SOC here. So there are many things that you can look at in the manufacturing, right? I just mentioned a couple. Again, insider threats are prevalent in the manufacturing, and testing phase follows that. And then you do have, again, during testing, you could have component replacement. Now, this testing could be pre-silicon emulation. It could be the hybrid emulation platforms. It could be the IP drag and drops that are happening. And then the complexity will also get in when you try to provision. That is the next phase in the life cycle. And when you're configuring, and as the SoCs get more complex, you now system on chips, you now have to provision the individual IP blocks within the SoC, right? The components within the SoC, and that there, you can introduce, like there are insider threats. And again, improper device settings is another thing. If you don't configure one IP correctly and completely, then that IP could actually be used. The intellectual property block within the SoC could be used as your Trojan, right? You compromise that and you leverage its properties and security, permissions to go attack the other ones, to attack the bus, to attack the fabric. And deployment, we all know, there are different things that can go wrong with the deployment. So the complexity it's actually spread out across these life cycle stages, and we have to slice it and then go attack them individually or tackle them individually. Yeah.
Anybody else on the panel want to say some things on this topic? I'm
I
sure
could,
you all have opinions.
Sure. Dan, you would like to take a shot? Go ahead.
Yeah, I was just going to comment on, the complexity of the chips and how the design process has really changed, going back to the 8080 to what we build today, and that's been enabled by our software tools, right? So today we use EDA tools to help us design our chips. These are incredibly complex software tools that are really good at optimizing the design for all sorts of different performance characteristics like power and size. But they're not very good, in my opinion, for optimizing for security. They don't have security built in the same way that they have these other things built in. And so the designers really, I think, struggle with that, and in some ways have to fight with their tools. So I think that's an active area of research right now, and trying to come up with ways to improve that. And one that I think is a good path that I'd certainly support.
Anand, you wanted to?
Yeah. I mean, I think I think a lot of great points have already been articulated. So I'll kind of step back and try to summarize, right? So I think the complexity is indeed mind-boggling, right? When you have these tens of billions of transistors on a chip. And I think the 3 points I'd like to make. First is, do not try to boil the ocean, right? You can't boil the ocean. So be strategic in terms of what your threat model is and what sorts of threats you're trying to protect against, right? When I was security architect for NEC's mobile application processors, it was like software attacks, right? Were our top 3 priorities, because that was the nature of the application, right? That's what we cared about, right? And so, but then a different chip, like a chip that goes into a defense system, it might be very different in terms of the priorities. So I think you need to really understand the stakeholders throughout the value chain for in your ecosystem, and understand what are your top priorities in terms of the threat you would like to protect against, and that would limit your scope. The second is divide and conquer, right? You may not be able to ensure that each of those transistors or logic gates in your chip is either not malicious or free of vulnerabilities, but start with that root of trust. I think it was Dan who talked about the root of trust. So make sure that that root of trust that is absolutely secure, right? And so concretely, when we were designing the mobile application processors, we were this is back in 1999, 2000. The industry first to embed a programmable security engine with an isolated execution environment inside that SoC. That, we went to great lengths to make sure that was secure, to minimize the complexity of firmware that ran on that processor, right? Of course, it wouldn't run a full OS and so on. And of course, that in a limited sense allowed us to insulate ourselves from the complexity of whatever was happening on the host and the rest of the system. So divide and conquer. And then the third is automate, right? I mean, like Dan said, I'm part of a program now called the ACE, Automatic Integration of Secure SoCs, funded by DARPA, led by Synopsys and ARM, our team, they are part of our team, where we are precisely trying to address that problem at the SoC architecture level, where through increased automation, we just reduce the possibility for human intervention, and therefore introduction of vulnerabilities either advertently or inadvertently. So increased automation Of course, that still means that you have to trust the tools, but hopefully that's a one-time job of ensuring or validating the tools. So I think that it's a combination of these three factors.
So can I add something real quick? So
Sure.
I mean, these are excellent points. I think I would just add that there are kind of two philosophies that I can think of. Like one would be essentially design in a modular way. So essentially to build up from kind of the baseline of very small functions, make sure that they perform exactly as intended under all use cases, essentially. And so then you can kind of like build up upon like existing work so that even though you have billions of transistors, it's built from a much smaller number of like high level components, and several of those may be trusted. But the other approach is to kind of use this attack surface definition and to really focus on like what are the specific attacks that are the biggest concern. And within those attacks, I would say there are two major types of like active attacks to worry about. There's the active attacks where there may be like approaches that are trying to directly cause faults. It might include things like using electromagnetic radiation to try to overpower or overwhelm your system. Or it could be passive attacks, like essentially like side channel attacks, where basically you're picking up something that's happening in the hardware that could affect information that you're extracting. So for example, you may be able to detect that certain computations are taking place remotely, even if you're not supposed to be able to know that information like on the network. And so those two different types of attacks require like two different mitigation strategies, essentially. And so if you know that one is more likely than the other, that's very helpful information to narrow down and avoid boiling the ocean, as Dr. Raghunathan mentioned. So thanks.
Let me sort of take a couple of these remarks and turn them into an observation and another question. We've seen in the software arena some of the same issues about how do we build a complex system and trustworthy in the process. And so part of it is to have assured components that we're able to put together. Usually there are problems at the interfaces or because they're reused in environments where the assumptions no longer properly match what actually is the use environment. And combined with that, we're seeing, I think, what at least from me as an observer of platforms over the years, there is a need for more and more speed and complexity in the hardware because we're competing and we've developed things in software, some of which we move into silicon, others that we just need more processors on a chip to execute. And of course, there's also the push for smaller die sizes. So there's this rush towards putting more on the chip, smaller die sizes, which, as you noted, Peter, also opens up to greater environmental vulnerability for some things, particularly in certain environments with radiation and EMF kind of faults. What we're doing is we're spending an awful lot building up complexity to probably make mistakes faster. And that certainly happens in software. And so we've also seen a consolidation. We see fewer chips that are available to be used as general purpose in a lot of systems. There's only 3 or 4 now that seem to be commonly used, and people are using those because that's what's available, rather than pushing for other kinds of custom chips. All of that to say, all of that as an environment, we're now at a position where we have only a few vendors for chips, few architectures that everything depends on, and small changes like the COVID problems result in massive disruptions of the supply chain. If a disaster were to befall Taiwan, very bad earthquake or a very bad neighbor, that could have an extremely severe impact on us. That's a different kind of security of microelectronics. I'd be interested in getting your comments as to how do we ensure against that, and how do we recover from that kind of problem where we're putting more and more dependence into a small number of very complex items. So is there, Dan, this in particular hits embedded systems right now. Automobiles are backed up for a long time, for instance. How would you like to take a shot at that first?
Sure. Yeah. So, I mean, there's a lot to unpack there, but, I think one of the big points you're touching on is, our access to electronics when, supply chain is disrupted. So, and that's really a separate issue from just, do you trust the parts that you're getting, right? Can you even get the parts that you need is a whole separate issue, and also a very important one. And I would say, the shortages that we're seeing now due to COVID are hopefully going to be, blips. The market should correct those types of changes. I think they're being caused mostly from shifts in consumer demand for things, and we'll see some correction. But the types of things that you said, or natural disaster in Taiwan or things like that, that could have much longer term effects, and is definitely a threat to be concerned about. And so I think for those things, there's really only one answer, in that we do need some amount of redundancy in the supply chain. And so at the beginning, I'd said, well, it's not as simple as just trying to reproduce the full supply chain domestically or elsewhere. But there is a need for that to some degree. And I think that's why, is that we do need some more redundancy in our microelectronic supply chain to try to address some of those access challenges.
Anyone else on the panel?
Yeah, if I were to make a comment, adding to what Dan said, I think the other thing that can be pursued is what we call a well-defined IP, or KPI bound IP, key performance indicators bound IP, that you can manufacture. So you define what you need, inputs and outputs of an IP block and certain KPIs, and then you go after wherever you can produce it, like redundancy that Dan was saying. I'm going one level below where, we could, that Intel started pursuing as well. And everybody, now it's organic now that the IP blocks could come from different, foundries, and, you could bring them and drop it into your SoC. So that's another way you could mitigate some of the availability, concerns as well. But that's one path to definitely to pursue.
Right. And so you're addressing the problem of not just the fact that the industry is consolidated, but on top of that, there's this problem of sort of like vendor lock-in, right? Where there might be multiple fabs that could produce a chip that would meet the performance requirements and functional, but when you design your chip, you kind of have to match your design to where it's going to be fabricated, right? And so, yes, that's a big problem. If we could break the vendor lock-in, that would go a long way.
Yeah. Although that's not something that I think too many vendors would embrace.
Yeah, but I was just going to add that I absolutely think redundancy is the way out, but it is an expensive option, particularly when it comes to redundancy in the manufacturing process or manufacturing supply chain. But it is something that we are seeing, maybe increasing acceptance of, because it's really, I agree with Dan, that's really the only way. Cutting edge fab is $20+ billion. We're seeing recent initiatives like the CHIPS or the USICA, I guess, the CHIPS and Endless Frontier Acts, really starting to address that through investment. So, globally, although if you just think from a global perspective, that might not be the most efficient way globally for the industry, it is a more robust way, and you pay in terms of, additional cost or investment. The other thing remark I wanted to make was that open source design, which is open source hardware, which is starting to pick up. Again, I know it's not going to be an easy push, because as Spaff just mentioned, it may not be in the interests of everybody, the various players in the computing industry, but I think trying to democratize the ability to do hardware design in general could be a good thing, at least from this perspective of trying to build in robustness.
Yeah, I've been intrigued by seeing some of what the Spark project that architecture. Although I don't see that being really embraced by anybody making it. It's been a very interesting kind of effort to go through. So this leads into a question that I had about, again, differentiation and consolidation. We have in the US, so I'll limit it to that, but we have need for trusted fabs, locations where we absolutely have no doubts about insider threat that several of you mentioned. And these are for critical systems, space systems, communication systems of national import. That's more expensive. And because it's a smaller customer base, it has a very different capitalization issue for trying to build those. That's probably too expensive to do for mass production of chips. But that brings up the idea of multiple levels of security, which we have with software, that some need to be more secure than others, higher assurance software, and we're willing to invest more. Can that model succeed in the current environment where we have such high capacity of chip demand and production? That idea of layered levels of security with different levels of assurance and effort put into ensuring resilience of the product?
It can, if I may start, it can give you certain immunity for certain temporal and spatial, right? But as you go and try to mitigate the more advanced threats, we have this concept of secure boot is where your hardware root of trust starts authenticating, right? Using that, you authenticate your very first instruction that gets executed on the CPU. And then that is where you're using hardware to trust software. Now, there is also this concept of software or firmware or software trusting the hardware, right? How does the firmware or software know that it is executing on a genuine hardware, right? So if you can somehow tackle or tie those together, yes, the upper layers can handle certain threats, and then at some point in time, though, when the hardware gets compromised, then during the next boot, or if it's a static root of trust or dynamic root of trust during the same boot, you could see the downward layers actually corrupting or tainting the upper layers, and then your system goes down. So it's only a matter of time. You can get temporary, kind of immunity on mitigations. Is what I think. Yeah.
Anyone else want to? I realize that was a poorly formed question, but hopefully, yeah. Anyone else?
Yeah, I mean, I definitely agree with Sunil. I think part of your question, though, if I understood correctly, is when you're talking about different levels of security. Part of that is you're saying, well, different levels even for the production of that hardware root of trust, right? So maybe we use a very expensive, trusted fab to build our root of trust, and that's appropriate for something that needs it. But we have other fabs that maybe aren't as trusted for other things. Is that
effectively?
Right?
So in a software world, using Windows for command and control of nuclear weapons and for keeping your recipes at home is a little bit different in nature, and we don't need the same. We shouldn't need the same system and the same level of assurance. So it's similar with hardware, right? Is that a commodity level PC probably does not need the same level of assurance as something that's going to go into a very critical medical or national defense application.
Right.
Does it make sense to distinguish those in the production environment and allocate resources accordingly.
I see. Yeah, I mean, I think it makes sense, but also, right, we can't ignore that that's exactly the philosophy of the Trusted Foundry program, which, you know, of course, was trying to put a lot of money into vetting certain foundries and saying that, you know, we know there's not an insider there, and, you know, this isn't appropriate for everything, but for the things that really need security, you can do that. And there've been a lot of problems with that program. Not the least of which is that it's incredibly expensive. So even for the systems that absolutely need it, it can sometimes be prohibitive, and it doesn't just always manifest in cost, but also in that the trusted foundries just don't necessarily keep up with the most advanced tech nodes, and because the market forces aren't there to let them keep up, and so you know, it's hard to look at that and ignore that and say that that's an approach that can continue to be used going forward. I think what we need to make something like that work is better ways to integrate. So maybe you do have something like that for your root of trust, but you need a better way to integrate that root of trust with a piece that's untrusted, that's built somewhere else, that's the most advanced tech node. Root of trust doesn't have to be the most advanced tech node, but if that then drives what the technology is for the rest of your chip, and you don't have a way to tightly integrate them, then that becomes really limiting for what you can build in that trusted manner.
So yeah, to add to that, I mean, that's a great point. And I think just to briefly explain, what does the zero trust method involve? That is a method that Dr. Raghunathan alluded to. And it basically means that you are able to source components from outside of like a trusted foundry type program, but then you conduct extensive verification and validation before you would include that in a more trusted system. And so you're not trusting the foundry itself, but you're trusting your process for taking that untrusted component and then confirming that it behaves the way that you expect before you put it into like an important application. And obviously you don't do that for like a computer holding recipes for home use, but you do that for like something that's much more critical for, you know, health and safety or what have you.
Yeah, and one example that comes to my mind is the MCP, multi-chip package, where you can pair an SoC along with an ASIC or a CPLD or an FPGA. And that FPGA or ASIC would have this secret sauce that would bootstrap the SoC and you know, does the handshaking and you know, enumeration and then periodic attestation. So in that way, you have this secret, you know, smaller IP that is actually bootstrapping a larger IP that even Dan was alluding to, right? Where your SoC, you will not be able to, you have to babysit basically, right? The SoC for the security perimeter purposes.
Yeah, I think heterogeneous integration is one promising direction, right? And advanced packaging technologies, because you know, it is becoming clear that it's going to be very difficult, or has, you know, become pretty much infeasible for the trusted foundries to keep up with the most cutting edge tech nodes. Now, not everything needs to be fabricated at the most cutting edge tech node, right? If your root of trust can be fabricated in that older process that is supported by the trusted foundry, and you can, you know, package it into a system, and thankfully for other reasons, right? Not necessarily relating to security. You know, for example, you know, AMD and Intel are really pushing, you know, to these technologies for advanced heterogeneous integration, you know, in the data center, you know, server class processor context. A lot of those technologies could trickle down and possibly be used here. And I think that's what Sunil was alluding to. I think that's actually a very interesting angle to maybe look at further.
It reminds me in part of the virtualization issue that we have, where we put the trust in the virtual machine monitor, and then we run all kinds of untrusted things inside of it. I'd like to return to part of, I think it was Dan's comment about the expense that people, it doesn't support the market. Is it possible that one of the problems we have is that customers don't understand the value of higher assurance? And if they did, we might be able to afford somewhat better methods or different methods. What is it about the current market that could be different? I'm asking you to speculate, but.
Sure. So, I mean, certainly today's consumers do not care much about security. I'll just say it bluntly. Security doesn't sell, and I don't think it's because you know, consumers are at fault in any way. It's a hard thing to look at a device and know how secure it is, right? I mean, a big part of my job is often doing that, and it takes a lot of work to make a good assessment of a device's security. And so it's not reasonable to expect that a consumer can make purchasing decisions based on something like that. So it doesn't sell. And I don't think there's an easy way to get to making it to sell. But yeah, that would have certainly improved the situation. One thing I could see happening that I hope will happen at some point is that security of electronics and computers in general go through something similar to what the automotive market went through with safety, where more standards are created and tests are standardized to where there's a ranking system, and it becomes much easier for someone to just look up, just like people can look up, how did this new car do on its crash test? How did this new phone do, this new smartphone that I'm going to trust to store all of my sensitive data, how did it do on its, hack test? And, if I can do that, then maybe now it can start to sell more. Maybe insurance companies can start to look at that as well for things like insuring big companies that store your data in the cloud, right? So I think through standards and tests and making that more easily available to a consumer, and then also making it hit some of the companies' wallets through insurance, that could be a path. But I think for the automotive industry, that took decades, and so it's probably going to be a long path for the same type of thing to happen with electronics.
We've been hoping for the insurance company to rescue the software industry security problem for over 2 decades, and it hasn't happened yet.
Yeah. If I can take another view to this, a totally different view, is where we should and we started doing the penetration testing at the architecture level, at the RTL level, and at the firmware level, and the operating system and the applications level, right? So both at the IP IP block level within an SoC and a system level, and we are just beginning to understand and qualify and quantify, if there are any escapes, security specific escapes. What is the cost of addressing them after the fact, right? So, a vulnerability, gets manifested, and then you actually now have to go back and fix it, whether it's a silicon stepping or a firmware change. Those are expensive, or a metal stepping. And what does that cost? And something like that. We are still feeling our way to qualify and quantify, right? But I think I completely agree with Dan that unless there is a Jeep incident for automotive that happened, Jeep hack that happened, Colonial Pipeline is an IT to OT wake up call, but still a small wake up call, I would say, right? A major grid incident would be a big wake up call. So unfortunately, I think the industry and everybody is waiting for those wake-up calls for their domains, right? Everybody is waking up at their own time, whereas we have to take all those security postures into considerations when we design, the SoC, the firmware, and everything else on the top of it. Right?
We've got a couple of questions that have started to come in here as we're nearing the end of our time, of course. So let me go through those. there are two that are somewhat related. There's one, could someone talk about the feasibility of a micro reference monitor or other component that could maintain an inventory of components and behaviors that could actually oversee and block behavior if it's out of the norm? And that's related to another question here, which is the idea of having different kind of IP blocks with different specific bounded capabilities, that we can have an open source SOC development kind of framework, that a standard that would address interconnections, data standards, voltage, and so on. So I think those two actually can go together, is looking at an architecture for both a monitor and for component integration. Is that feasible? And what do you see as the likelihood of success of something like that?
Yeah, so I don't know if, so there are some, there's a technology, I can speak from Intel side of things, called threat detection technology that Intel created, that actually lets you capture, it's a machine learning based technology that lets you train on the known patterns of execution. And then when there is an anomaly, then that anomaly gets detected. And then, you know, there is some some policy enforcement that you can definitely take. All right. So that's one method, and I'll pause for others' comments. Yeah.
On the second part,
go ahead.
Go ahead, Peter.
No, you go first.
Oh, I was just going to say that on the second part of that question about standards for open, like sort of IP interconnection, there are a lot of standards, right? Particularly at the SoC level. I think at the chiplet level, it's emerging, but certainly at the SoC level, there are open bus standards, right? Or standards that you can design too. And of course, you can have IPs designed around those SoC standards. The most pervasive, just historically, because it's been more, I guess, the most used in IP-based SoC design is the ARM, like AMBA or AXI, ARM-based standards. But every company has their standards, and many of them are open source. So I think that is something that already sort of exists, supporting interconnections. What it could be an interesting angle is to see how security could be built into that interconnect fabric itself. Right? If you look at, for example, again, I'm familiar with the ARM trust zone, it layers security on top of the on-chip communication, the interconnect, by having dedicated signaling in there so that components could, for example, discern between transactions as being secure versus non-secure. That's just the starting. There's many other levels of functionality, right? I think as what Sunil was mentioning, you could imagine that interconnect fabric itself being intelligent enough to monitor the transactions taking place between the different components, and maybe detecting anomalies and even blocking off components. And we at least in the research domain tried out some of these things back during my days at NEC, and so I think there's a lot of possibilities in that direction. I think particularly when we get into the domain of provisioning IP, I think that can again the interconnect fabric can play more and more of an active role and have a richer role to play in security.
Okay, so those are great comments. And so I would add that there are a number of startups that are interested in kind of making it easier to develop open source system on chip designs, which can include secure opportunities. So eFabless is one that comes to mind. There's also like a lot of work on developing on a RISC-V design platform. And there's an open SoC system architect work. So there's a lot of work out there. And I did also want to add that in terms of enforcing like a zero trust model, there is actually a NIST publication, and I think the number is NIST 800-207, and that was actually like mandated by the Biden government in May 2021 as being required for US federal agencies to adhere to this protocol. And you can look it up. It's like open for the public to read and kind of see what the framework is. And I think it could be helpful to understand like one potential implementation.
All right. Well, I think we could go a little longer. We still had a couple questions, but we have run almost out of time. I wanted to give each of you a chance to sort of do a 90-second summary along with what do you think are the top 2 things that we can do in academia with industry partners to move this field along. So let me sort of go here in backwards order. I think it was Peter was the first one or the last one in the introduction. So you want to take that?
Sure. So I would say in summary, there are a lot of challenges in terms of developing trusted and reliable hardware, but it's also a very critical challenge to take on. And of course, there are a lot of opportunities here, but I think that making it fundamentally more accessible to model the most important risk vectors and to work more effectively with open source and off-the-shelf hardware are going to be key directions. And so in terms of research opportunities, I think that's going to be a huge emphasis in terms of getting researchers in academia working more closely with the federal government and industry to develop solutions that actually have practical implications for solving some of these security challenges that we talked about today.
Okay. Dan?
Yeah, so that's a tough question. I'm thankful that I had a minute to think about this while Peter was talking. I think, so 2 top things. There's definitely a need for just more research and developing new techniques that go along with that zero trust paradigm where, you know, you're accepting the fact that your fabrication facility might try to do something nasty to you, but you're building in techniques that make your system resilient anyways. I think there's a lot of room for developing new techniques in that area and in maturing the ones that we already have. And so I guess I'd say my number 2 is, as we do those things, we work closely. The folks in academia that are coming up with these great ideas work very closely with industry partners to make sure that they understand the practical issues that some of those techniques then create, and think about how to overcome those, because I think there's a lot of great ideas in academia that have a hard time, you know, getting off the ground because we're not thinking about the full I guess stack and how to actually make these things practical.
Thanks. Anand?
Yeah, no, it's definitely a very exciting time to be in the space, you know, because of the broader interest, both commercially and from, you know, the government and DoD side of things. So it is a very challenging problem. For example, I know DARPA has been investing in this specific issue of, you know, how do you ensure that chips are free of Trojans, free of side channel vulnerabilities for almost 15, 20 years. You know, it is not a solved problem. I think it will require a cooperative effort, like Peter alluded to, both across, you know, academia, industry, but also across the different players involved in the chip design process. So I think you know, that's my comment, you know, sort of more broadly. And I think one great example of how academia and, you know, industry and the government are coming together is our CSME Center. Joel, thanks for sharing the link to that center earlier on, you know, where we are, you know, really trying to work with both industry partners and stakeholders from the DoD in both, you know, advancing research, but also training the next generation of workforce. That's something that we didn't address as much. At the end of the day, you know, we need the next generation of designers to really be aware of security and, you know, build in or think about security as they're designing the next generation of hardware systems.
Thank you. And Sunil, will you close out with your thoughts?
Yes. So one thing that I want all of us to focus on is a compute lifecycle assurance, CLA as we call it, right? So that's what will get us to focus on all the phases, right, throughout the life cycle. And then the other thing is we talked a lot about zero trust, right? So I'm not sure, you know, I want to bring one micro focus to it is IP to IP, right? How does within an SOC, if you take an IP, for example, we can assume that, maybe when the SOC gets attacked and the IP blocks start getting compromised, let's assume that if even 70% of them are still intact, they can actually account and vouch for the other 30% bad actors, right? So establishing zero trust and maintaining it between the IP blocks within an SOC is something that's really rich for research, right for research. And then the other thing is, if there are any ideas, innovative ideas, for example, the compiler problem today, right? So how do we, even for a software land, how do you know that the compiler is not producing, right, buggy code, right, intentionally, right? And so the same problem goes along with these other tool chains and everything in the hardware side, RTL, right? There are tools that actually, check the RTL. How do you know that the tool is not compromised itself? How do you check the tool? So there's got to be some formal methodologies that we should work together to make sure that we can check the checker, right? Or check the compiler or things like that. So, yeah.
All right. Well, thank you all. This is a fascinating topic, and I know we could go on longer, but we have to stay on schedule. So let me turn it back to Joel.